Today we're going to talk about accuracy versus precision, or accuracy and precision. People tend to think these two terms mean the same thing, and it's really hard in the beginning to see why they're different, because I think just in English we treat them the same, but scientists don't. Accuracy, that is an ACY at the end, although you probably can't tell, is how close a set of measurements are to the true or accepted value. So for instance, if you were calculating the density of pennies, and if the pennies were full of aluminum, say, which they're not, and you were getting densities of around 2.7 for each set of pennies, that would be a very accurate number. All right, so you got 2.68, 2.71, 2.70, 2.71 again. Those are accurate. They're close to the true value of 2.70, and those numbers would actually be precise as well, because they would be close to each other. That's the definition of precision, how close a set of measurements are to each other. Now, suppose you were weighing yourself every morning. You were trying to gain or lose weight, and you were getting on the scale every day, but you were getting on the scale with all of your clothes and a pair of big, heavy boots on while you were carrying your backpack. Okay, so every day you're getting a measurement of your weight, and it's not changing, but it's also not really, never mind. That would be accuracy. They're not really close to the true value because you're carrying an extra 20 pounds of stuff. However, if you were weighing the same amount every morning, even though the number was wrong, and if every morning you got on the scale with all this extra stuff and you weighed 150 pounds, even though you really weigh 125, it would be precise. So, again, I've confused you more than I should by talking, so let's look at some pictures that are always in books. Now, you would think because I'm at home and because I had time, I could make decent circles, but that is not the case. So these circles represent targets, with the center being a bullseye, and you are playing darts, and you are aiming for the bullseye. All right, and these circles also can be thought of as having an axis system in them, like this, where we have, the plus x-axis and the negative x-axis and the plus y and the negative y, because we're going to need to be thinking like that in a minute. So if you look at these four dots, these four places where your dart has hit the target, you see that these darts are all clustered, but they're not where they're supposed to be, which is the target. Since they're close together, they are precise. Since they are not at the center of the target, they are not accurate. So this group here is precise, but not accurate. Okay, that's the first one. So let's go over to this one. So you threw your darts at this target, and they're all clustered together, which means they're precise, they're close to each other. And they're actually where they're supposed to be. You were aiming for the bullseye, and you got close to the bullseye. So these are both precise and accurate. Now, look at these guys. You might go, these are just an absolute mess, which they are, but if they were data points, it wouldn't look that way. If you think again about the x and the y axes, positive and negative x and y, if you average these two on the x-axis, they'd be right there in the center. And if you average these two, that would be on the y-axis, with the origin being the bullseye, they would also be right there. These four values are not close together, so they are not precise. But when you take the average of those values, say plus 3, minus 3, minus 3, they would in fact be accurate. So not precise, but they are accurate. And then these last guys over here. These are truly a disaster. Okay, if you did the average value of these, it'd probably be somewhere around there where I made the X. They are not clustered together, so they are not precise. And the average value isn't anywhere near the bullseye, so they're not accurate either. So we've got precise but not accurate, both precise and accurate, numbers that are not precise but are accurate, which is a very common situation for students to have when they do labs, that they'll get numbers that are just kind of all over the place, but they happen to give you the right answer. And then you can get numbers that are just a plain disaster, neither accurate nor precise. Okay, and so how do we measure accuracy? You measure accuracy by knowing the percent error. And the percent error compares the true value of something to the experimental error, or value, sorry. Okay, so instead of looking at targets and darts, we're going to actually do numerical comparison. So the true value is something that is known or something you can look up. Okay, it's a known, established value for something. And the experimental value is something you would determine in lab. And the equation for finding percent error is just this. Percent error equals the absolute value of the true value minus the experimental. EXP just stands for experimental because I am being lazy, over the true value times 100. Your book may flip these around and say experimental versus true. I had always been taught that you take the absolute value and that this is always positive. Okay, that you're not going to have negative percent errors. So it can either be experimental versus true or true versus experimental because you are going to take the absolute value of that difference. You're going to then divide by the true value and multiply by 100. So for instance, talking about aluminum, the density of aluminum is 2.7 grams per cubic centimeter. That's the known value. I think it's actually 2.0, but I'm not positive. And a student doing a lab, like your penny lab, the student has a density equal to 2.9 grams per cubic centimeter. And the student has been asked to calculate the percent error. So you put the true value in, so I have the absolute value of the true value minus the experimental value. That's going to be 0.2 divided by the true value, all times 100. So I'd subtract these two since it's the absolute value. It's not negative 0.2, it's 2. Or excuse me, it's not negative 0.2, it's a positive 0.2. I'm going to subtract 0.2 by 2.7 and then divide or multiply by 100, and I get 7.4% as my percent error. Usually anything less than 10% for you guys in high school is considered pretty good. So accuracy versus precision, and then how to numerically measure your accuracy. And that's it for today.